I'm not dreaming anymore. All that I know is I'm falling, falling, falling.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. As an example of an elastic collision, we are looking at what happens when a neutron, for example in a fission reactor, hits a nucleus of some kind. This is usually called the moderator substance, which can be graphite or water. Well, it can be anything, but those two are mostly being used in fission reactors. And the idea why moderators are used is that in order for a fission reactor to happen, fast neutrons are not good. Slow ones are better because they linger in the vicinity of the fuel, which is usually uranium, and by lingering there longer time, they are more likely to cause fission in the uranium. So when we are trying to slow down these neutrons, what kind of substances should we use? And we can partially answer that question by simply studying elastic collision between these two. So first of all, we have neutron coming in at some velocity Vn1, and the target nucleus is sitting still. Let's assume that. First of all, why is this collision elastic? Well, the two nuclei are being repelled by the positive charges of these two, and the electric force known as Coulomb's force is indeed a conservative force. So energy in this kind of collision is conserved. And let's state our conservation of energy in the form that we learned for elastic collisions. So we know that the relative velocity, this is the velocity of the target nucleus afterwards, minus the velocity of neutron afterwards, that is the relative velocity is same as the initial relative velocity, so that's v of target 1 minus v neutron 1, with the distinction that we have the negative sign here. So magnitudes are the same, but the direction is reversed. And we can solve for, let's solve for v2, the velocity of the target nucleus, because we are trying to eliminate this factor or term. So we get, first of all, the v target 1 is 0, so we have only Vn1 plus Vn2. So this is from conservation of energy. Then conservation of momentum. So initial momentum is only that of the neutron, so mass of neutron times its velocity must equal the mass of neutron and its velocity afterwards, that is the momentum afterwards, plus the momentum of the target nucleus. So that's m target times v target after the collision. And let's plug that in. So we get mn vn1 equals mn vn2 plus mt times vn1 plus vn2, and we'll open that one up. So mn vn1 mn vn2, oh, let's bring that one to the, oh no, let's keep it there, vn2 plus mt vn1 plus mt vn2, and now bring everything with the Vn1 to the left hand side and keep the Vn2s on the right hand side. So Vn1s we have, take that as a common factor, we have Mn from here minus Mt, mass of the target from there. Same thing on the other side, so they have Vn2 as a common factor, so that's going to be mass of the neutron plus here mass of the target. And then we get for the velocity of the neutron after the collision Vn2 to be initial velocity times Mn minus M target divided by Mn plus M target. Let's calculate some values. So let's consider we had water as the target nucleus, H2O. So mass of H2O in that case, or the mass of the target would be, that's 18 atomic units, 16 from the oxygen and 2 from the hydrogens. And the mass of neutron is just basically, well, it is 1 atomic mass unit. And if we put that in here, so for H2O, we would get Vn2 to be Vn1, and then Mn, mass of neutron, that's 1U minus 18 from the target, divided by 1U plus Mt, so 18. So this is Vn1, and have a negative sign there of 17 over 19. So this tells that the neutron will bounce in the opposite direction because of the minus sign. We still have 17 over 19, which is about 89% of the initial, well, let's do it this way. So about 89% of the initial velocity. How can we improve this situation? So let's look at this formula. If the mass of the target would be the same as the mass of the neutron, then the neutron velocity would be 0. And in fact, hydrogen, which is pretty much just one neutron. Oh, it's basically 1 proton that has about the mass of 1 neutron, is indeed a very effective moderator. If you think about this, this is exactly like playing pool. So we have 2 balls that have equal masses, and if the neutron would be the cue ball, it would hit the target, and the cue ball would stop like hitting a wall, and the target nucleus in this case starts off with the same velocity as the neutron had. And that is the property of an elastic collision, to have the most energy transfer from the incoming object to the other one. You want them to have the same mass.
Oh.